Okay, for this problem, the directive is to launch a horizontal projectile and figure out what's going on. So I'm just going to predict we have an object here. We're going to launch it straight sideways. We're going to launch it at 10 meters per second. Let's pick a building elevation of, I don't know, 20 meters. And by solve it, that might mean, well, find something out that you don't know. In this case, probably the most logical thing would be to think about where it's going to land. We know it begins to fall immediately, and that should be a really nice smooth parabola. We'll see how well I can draw a nice smooth parabola today. That's a little better. And the goal is, as it falls, we want to think about what happens to it. We know acceleration in the vertical direction is going to be g. We know acceleration horizontally is going to be 0. So we know that nothing's going to change horizontally, and vertically it'll get faster and faster. If we want to figure out where it lands, we're really asking ourselves, hey, what's this distance? And that's dx. So I'm going to write an equation for that. dx, well, the final dx position, I grabbed the one off my tattoo, right, is the initial dx position plus v initial x times t plus 1/2 ax t squared. I just wrote the entire kinematics equation out. I always like to start with a whole equation, and then we can decide if anything goes away. Let's name our starting point up here the origin, 0, 0. That means that my dx initial is going to be 0. The initial speed horizontally, that's 10. That's not 0, so that's 10 meters per second squared v initial x. But the acceleration horizontal we've spoken of as 0 as well. So now if we clean this up a little bit, hey, we're trying to figure out the final position. Well, it just comes down to that's the initial speed, which we know is 10 times the time, and that's it. Now the problem is we're stuck because we don't know the time, and we can't get the time from this equation because there's not anything else we know. So the goal now is to switch and to think about the vertical scenario and write a vertical equation from which we can come up with a time. So let's go ahead and do that. So let's write the same thing vertically given what we know. We know that dy final is dy initial plus v initial y t plus 1/2 a y t squared. Exact same equation, just put in everything we know. Again, the starting point, we're going to call it 0, so we're going to call this 0. The initial velocities, let's talk about those. V initial y and v initial x. Well, we know the thing is moving in the x direction, so we know that's 10. But in the y direction, its initial velocity is 0 because it's launched horizontally, not vertically, so it's 0. So that means this part's going to go away. And all we're left with in this tool is the last part, dyf. Hey, we know what that is. That's how tall it is. 1/2 a t squared. And we know what a is because that's gravitation. All right, so I'm going to decide that positive is down in this case, which will make dyf 20 meters. I know acceleration is also in the downward direction. I'm going to call that a positive g, and that allows us to solve for t. So t, in general, you're going to see this tool 2 times d over g square root. Yeah? In other words, in this case, it's 2 times 20, which is 40, divided by roughly 10, which is 4. So it's going to be about the square root of 4. I made this fairly convenient because that, of course, is a nice 2 seconds. Hey, once we know that, we jump back up here, we drop it in, and we solve the problem. V initial x, 10 meters per second. Time in the air we figured out was 2 seconds. Hey, it sounds like it's going to go a nice, clean, even 20 meters. Ooh, that's very convenient. It's very symmetrical too, but we now know that this distance traveled is going to be 20 meters. Hey, there is a quick horizontal launch problem.